Hi, these are edited versions of the lectures that I taught synchronously over Zoom. I hope you find them useful. This is lecture 12, and we're going to talk about uniformity of subsampling today. So to connect with what we did before, last class we talked about saving the t-test, right? We had the result from Bahadur-Savage that you cannot test hypothesis about the mean. Then we learned that was a universal problem if the family of distributions was too big. And then, we particularly care about the t-test because we use it all the time in regression and, difference in means type of testing and etc. And so we try to discuss possibilities. We talk about distributions with compact support. We mentioned, but we didn't prove symmetric distributions. And, those led to situations where it was possible, but not through the t-test. So later on, we introduced these distributions that were uniformly integrable, or what we call 2 plus delta moments. And so there we proved that the t-test was uniformly valid and that it had power against local alternatives. So we're back, and then we know then the conditions under which the t-test works really well. So today we're going to start talking about resampling in general, and they're going to learn about or try to think about uniformity in resampling, and I'm going to talk about subsampling. And then why I want to talk about subsampling, you could have said, well, you should have started with the Bootstrap. You could, but the story that I'm going to tell is more aligned to how things evolve in the literature of moment inequalities, and is going to be closer to the situation that I want to describe today. Paying particular attention to the so-called parameter at the boundary example, which we'll see later, is going to be related to the problems that you run into in the moment inequalities literature. And so what we're going to see today is that in examples that are not smooth, and then parameter at the boundary is going to be one of them, the Bootstrap fails, and it fails point-wise. Okay, so it's not that it fails uniformly, it just fails point-wise. In those situations, subsampling, okay, in those situations, subsampling came as a rescue, and was introduced as the resampling method that does not require the conditions that the Bootstrap needs. And whenever the Bootstrap fails, subsampling is going to work. And that's how a lot of papers in problems that are related, for example, to the ones that I'm going to talk about next class on moment inequalities, started with subsampling from the get-go, because people knew the Bootstrap doesn't work, subsampling does. And then what we're going to see today is like, okay, the Bootstrap failed point-wise and subsampling works point-wise. Is it really the case that subsampling here also works uniformly well? And the answer is going to be, it depends on the problem, okay? And hopefully we'll understand what are the driving features that make the problem good or bad. So I'm going to start by reviewing subsampling. And just for the sake of transparency, the first 3-4 slides are going to be exactly the same that I cover in 480. But I know that if I just come here and say like, hey, remember what I said in 480, some of you will start putting faces. So let's just redo it. So the data is going to be just X. Whoops. Whoa. I don't want to record myself. Shut up. Now I start this pop-up thing that I don't want. All right, let's start over. The data is going to be this X1 through Xn sample of ID observations from some distribution P in role P. The parameter of interest is going to be some real value functional theta of P. I don't care particularly what it is. The important thing is that there's going to be an estimator that we're going to denote by theta hat n, which is a function of the sample, and we're going to have a root. The root here I'm going to denote it by Tn, going to be a square root n, theta hat n minus theta p, where root, again, if you forgot our terminology that we introduced in 480, stands for a functional that depends on both the data and theta p. Okay. Then I'm going to use the notation J and P to denote the sampling distribution of the root finite sample distribution of the root, right? So here there's an n here, there's an n here. We're talking about finite sample distributions. And then J n x p is going to be just the CDF of that root. And it's going to be, again, the finite sample root. The goal for us is to estimate this CDF, because if we have this object, then we can do inference on theta by exploiting this feature. Okay, for example, we want to use the quantiles of this distribution to construct a confidence set for theta, or to test that theta is equal to 3, and so on. The problem is that we do not know P, and since we do not know P, we do not know JNXP. Even if we knew P, this could be difficult, but the problem is even worse than that, which we don't know P. Okay. So Bootstrap solved this problem by replacing P by P hat, where P hat n was the empirical distribution of data, which essentially is the distribution that put mass 1 over n on each of the observations. Okay. And then what we learned in 4.8 is that a condition for the Bootstrap to work was essentially to say that this JNXP, when viewed as a function of P, was continuous in a suitable sense in a neighborhood of P. Okay, so the idea again was, you can show, that the empirical distribution P hat n converges to P, so P hat n gets close to P, and if this distribution J of n xm P hat, then we'll get close to JNXP because it is continuous. Well, we also learned that an alternative to the Bootstrap known as subsampling was due to Politis and Romano, does not impose this requirement, this continuity requirement over here, but rather it just needs this assumption that we're introducing in 480, which says there exists a limit law JP such that Jn converges weakly to JP as n goes to infinity. So you need this distribution to have a limiting distribution. That's it. And if this holds, this does hold subsampling needs, and it doesn't require any continuity of the like. So in any setting that is quote unquote not smooth and the discontinuities are present, you would expect the Bootstrap to fail, whereas subsampling doesn't really need that to be valid. Okay, so that's what we know. The intuition behind subsampling, I'm going to go briefly because I said this, but in case you forgot, because we're going to be manipulating objects like this today, is that suppose for the time being that theta p is known, okay, and suppose that you had a really big sample size m, such that in reality what we have is k samples of size n, which is the object that we want. And we have a very big k, so that means we have many samples of size n. Then what we would do is we would estimate the distribution that we care about by just using each of the samples of size n, okay, computing this object, square root n, we know, theta hat, we know, and theta p, we know, because we're assuming this over here. And then we have k of these elements. And so then now you have essentially k draws from this distribution, and by Glivenko-Cantelli, then we know that we can estimate this by using, the empirical CDF, essentially. And so we also show that considering just the sets that are disjoint is not the best that you can do. There's an improvement possible if you should consider all possible subsets of size n from the n observations. How many of those you have? M, choose n. And then you do this and you estimate, the distribution that you care about by using all these observations here that, despite not being independent now, there are a lot more, and you can show that in the end you end up winning by using more, even if they're not fully independent. That's the intuition behind subsampling, and this is what I know that essentially triggered the intuition behind the actual approach. This thought experiment where you said, what if I had this situation, then I would do this. And so then the difficulty is to realize that this never happens, right? That you never have a lot of samples of size n. So what do you do instead? Well, as I wrote here, in practice, m is equal to n. So you only have one sample of size n. So this idea will not work. But the key idea is to replace n with some smaller number, b. okay, that is much smaller than n. So you say, you know what, instead of estimating the object that I want very well, I can estimate a similar object or another object that I don't really want very well. And so what you can do is you can estimate the distribution of size b, which is the square root b theta hat b minus theta p, where theta hat b is the estimate of theta p computed using the j set of data of size b, okay? So, and if you do this, you're going to have a lot of these objects, okay, and choose b. And then you can use all these random variables to estimate this distribution well using the empirical CDF. That's nice because then you realize that you can estimate JB really well. The problem is that you really want JN, not JB. So what you need is some way to force JN and JB to be close to one another. And how do you do that? You do that by the assumption that we wrote before that said that Jn converges and distributes to some limit Jn Jxp. Okay, and if both Jb and Jn converge to the same limit as b goes to infinity here and as j goes to infinity here, then if you compute the difference between Jb and Jn and you just do triangle inequality, you end up with these two terms, right? And this one over here will just go to 0 as b goes to infinity, and this one over here will go to 0 as n goes to infinity. And so you realize here that you need a large sample size, you need a large b, but you also need n choose b to be large, right? Because you want to be able to estimate the distribution JB well. And so subsampling essentially imposes conditions so that all these three things happen. Of course, the first one being just the sample size being large. So we need both b and n choose b large. And so it is sufficient to assume then that b goes to infinity, which is called the block size or the subsampling size, and b over n goes to 0, okay? Meaning, it's much smaller than n. And then, the procedure work if we do not know theta. We said everything about knowing theta, but this actually works if we don't know theta, okay? But we can replace theta p with theta hat, the full sample estimator, okay? And the reason is because if you just look at theta b, theta hat minus theta p, then this is small. And it follows because this guy over here is small. To see this, if it's not clear, notice that you have square root b, okay, theta hat, what's the terminology? B, j minus theta hat n. Well, this square root b, theta hat b, j minus theta p minus square root b, theta hat n minus theta p, and this guy over here is the one that is square root b divided by square root n times square root n theta hat n minus theta p. And the full sample estimator converges array square root n. So this guy is big OP1. So this is, square root bn times big OP1, which is little OP1, because it's the assumption that b over n goes to 0. So using the true theta p or using the full sample theta hat p is asymptotically equivalent, okay? Now, for testing, quite often we're going to just use theta p, because under the null hypothesis, if you want to test theta p is equal to 3, okay, well, you're going to plug in 3 here, and that's how you're going to do it, okay? But in other settings, that may not be what you want, and then replacing theta hat with theta p works. So nothing of what we said depends on the fact that theta p is known. So notice that all we require was that j and xp conversion distribution to a limit distribution jxp without the n. And the bootstrap required this plus the condition that this distribution was continuous in a certain sense. Okay? And so showing continuity of this distribution is very problem specific. And it's the part that essentially, when you just look at papers that are complicated, where people come with like sophisticated things, and then they say like, well, we don't know how to compute standard errors, so we're going to do the bootstrap. Okay. And people ask like, wait, are you sure the bootstrap works in your setting? When people ask that question, and if it's say Joel, they mean this. Okay. This continuity. Which is a very fair question, because the bootstrap doesn't work magically. It requires this condition, okay? And by now, as I said, like it's how aware people are of this possible failure of the bootstrap is pretty much field specific, okay? If you're doing I/O, people in I/O are so used to the fact that the bootstrap fails in a lot of their settings that, they're very worried about using the bootstrap if they don't know what's going on, because the next thing they know is here comes a paper saying that the bootstrap fails in your setting. Okay, so they're aware of that. But if you just go to other fields, labor, public, development, also problems tend to be more standard there, not to mention macro. People just use the bootstrap and typically don't show much concerns of the possibility that the bootstrap fails. Okay. But, when somebody asks, hey, if the bootstrap works in your setting, this is exactly what it means. Okay. Okay. Subsampling doesn't need this. And so the theorem is the following. The theorem says, and I'm going to tell you why I'm running this theorem here again. Just let's read it out loud. Assumption A holds, okay, which is the condition that you have a limiting distribution, that J and P denote the sampling distribution of the root that we care about. Notice that here, for sake of being general, we're including a rate that could be a non-parametric rate or whatever. It doesn't have to be a square root n. So it says here, for some normalizing sequence tau n going to infinity, and then capital N is n choose B. We're going to assume that tau B over tau n goes to 0, B goes to infinity, and B over n goes to 0 as n goes to infinity. And then you essentially have 3 results. Okay, the first one says that the empirical CDF of the subsampling object, okay, converges to the limiting distribution J in probability. The second one says if this distribution is continuous, then the convergence is uniformly. Okay, so here I forgot to say, of course, we're assuming X is a continuity point. And then the last one, which is the one that you use for inference most of the time, determines 2 quantiles, the quantile of the distribution L here, and the quantile of the limiting distribution J. And then it says if this distribution is continuous at the quantile, then the probability that your root is less than or equal than the critical value converges to 1 minus alpha, where the critical value is the one that you obtain via subsampling, is the 1 minus alpha quantile of your subsampling distribution. Okay? So using a quantile of a distribution of size B is valid for an object that has a distribution of size n. What I want to say here is that this theorem is pointwise. Notice how P is fixed everywhere. Here's B, here's B, here's B, okay? And so it's not uniform in any way. Questions about this before we move into the new topics? Uniformity issues with subsampling. So Andrews and Wimberger in a 2010 paper studied the properties of subsampling in a broad class of non-regular models. This was at that time, Don Andrews and Patrick Wimberger had a lot of papers talking about different properties of subsampling and all related uniformity problems. More recently, also, there's a paper by Joe Romano and Asim Sheikh that presents conditions that are different than the ones presented in Andrews and Wimberger to understand when the bootstrap and subsampling could be uniformly valid. Okay, but I'm not going to talk about those. What Andrews and Wimberger did, they consider cases in which the statistic has a discontinuity in its asymptotic distribution. That's the thing I put in blue over here, as a function of the true distribution that generates the observations, which is P. Okay, In such cases, the Bootstrap typically procedures do not provide pointwise asymptotically valid inference. Okay, so as I said earlier, when people think about where the Bootstrap works or fails, they are thinking about pointwise behavior. Okay, so when then let's say when the model is complicated like this, the Bootstrap is not pointwise valid. And as I said earlier, for such problems, subsampling has been advocated. Okay, because look, if the Bootstrap fails, just go for subsampling. Okay, because of the previous theorem that we just showed. But the arguments in favor had been based on pointwise asymptotics, which is the theorem that I showed you in the previous slide. So what we're going to do now is we're going to start with a simple example, and we're going to do 80% of today's class on this example, which is a parameter at the boundary example. We're going to use this example to show that the Bootstrap fails pointwise, okay? And then we're going to show that subsampling in this example is valid pointwise, and then we're going to try to understand what are the properties of subsampling when we think about it uniformly. And we're going to learn what are the right sequences that you need to think about when you want to study subsampling in different settings. Once we're done with this, we're going to essentially introduce the general result that was proposed or presented or derived by Andrews and Guggenberger. Parameter boundary. It says the following. Suppose you have IID sample from some random variable with distribution P. Notice here the bold P family is normals with means theta P and variance equal to 1. So it's just very simple. But this is a family of distributions where the mean is known to be non-negative. Okay, so theta P is greater than or equal to 0. That's the family of distributions. If you do maximum likelihood immediately gives that the maximum likelihood estimator is the maximum between the sample mean and the 0. And so we're going to consider the root that we typically use, which is square root n theta hat minus theta p. And this trick that I'm showing here, we're going to do over and over. So hopefully it's transparent. This is just replace the estimator. You have square root n maximum of the sample mean and 0 minus theta p. Okay, now take the theta p inside the maximum, okay, and then multiply by square root n. So you have maximum of square root n x minus theta p here, and then here where the 0 was, you have negative square root n theta p, which is what happens when you put that theta p inside. And so what's the limiting distribution of this? Well, it depends on the value of theta p. If theta p is 0, you have the maximum of this object and 0, and this object here converges by the CLT, okay, to standard normal random variable that I'm denoting by Z, okay? And so if theta p is 0, this converges to the maximum between a standard normal and 0. Now, if theta p is positive, then you're multiplying here by square root n. So this is drifting this term to negative infinity. And so this just converges to a normal, okay? And so you have this distribution. It's just this maximum if 0, and it's normal if it's positive. For reasons that will be clear later, I'm going to denote this limiting distribution by J0, this one, and J infinity over here. And in a minute, this is going to be clear about what I'm going to be using this terminology. So as I wrote below, before moving to subsampling, we will show that this, which is the Bootstrap approximation to this distribution, does not converge to this limit, almost surely. Okay? In other words, Bootstrap, and notice that here I'm keeping this P over here fixed. So this is pointwise in P. I'm going to show that the Bootstrap fails pointwise. So for each n, we're going to use this triangular array business. X and I is just going to be, again, an ID of IID random variables with distributions Pn, okay? Which doesn't necessarily need to be in bold P. And then we're going to assume that this distribution satisfies 3 properties. 1, Pn conversion distribution to P. 2, theta P conversion distribution to theta Pn conversion distribution to theta P. and 3, the variance, sigma squared Pn converging distribution to theta P. The distribution JNXPN, okay, is this distribution that we have over here at the bottom, where you just estimate your parameter using the observations that come from Pn. You subtract the parameter under the distribution Pn, do the same trick, and then we have this business here where we have this object that is going to converge in distribution to a standard normal random variable, okay, under Pn. And then this object over here that we don't know because now Pn is a sequence, right? And so, I don't know. But I say, suppose without loss of generality that theta P is 0, okay? Not theta Pn. Theta P is 0. And let's make this assumption over here. Suppose that square root n theta Pn is greater than some constant c for all n. If that is the case, okay, there's an assumption. Suppose if that's the case, then Tn here is less than or equal than the maximum between this object and negative c, okay, because we have this inequality here. So, notice here that then this means that negative square root n theta Pn is less than negative c, right? And so we have this situation here where the distribution JNXPN converges here. So the distribution is the maximum between a normal and negative c. Distribution is dominated by the distribution max of c equal to 0. So you may say, like, how is this related to the bootstrap? And I said this is a way to think about the bootstrap, which is try to prove your results with a non-random sequence of distributions Pn. And if you find what you need from the non-random sequence of distributions Pn, which is usually simple to do, then you complete the argument by showing that the empirical distribution satisfies the requirements you impose on Pn. And here we have 4. 1, 2, 3, 4. So we managed to prove that the empirical distribution of the data, which is the one that you use to implement the bootstrap, satisfies 1, 2, 3, 4 almost surely. Then we show that the bootstrap is going to converge here almost surely, and then it's just going to be invalid. So let's do that. 1, 2, 3 is immediate. Okay. Law of large numbers gives you 1, 2, 3. So nothing to prove there. The part that is trickier is 4. So I wrote here, it remains to determine whether square root n theta hat p hat n is greater than c for all n almost surely. Equivalently, we need to determine whether x bar n is greater than c over square root n for all n almost surely. And I wrote, unfortunately, the strong law of large numbers will not suffice for this purpose. Instead, we will need the following refinement of the strong law of large numbers, known as the Law of Iterated Logarithm, that I'm sure you covered with Joel in 480-2. And if you're still dreaming about it, that's the effect of 480-2, right? So, said theorem that y from 1 to n be ID sequence of random variables with distribution p on the real line. Suppose that the mean of p is 0 and that the variance is 1. Then we have that the lim sup of the sample mean divided by square root of 2 log n divided by n equals 1 almost surely, and the lim inf equals to negative 1. Okay, not going to use the lim inf, but I'm going to deal with this part of the theorem. And with this, I want to be able to show that this over here happens, which, as I said, is equivalent to this. And this sort of like follows immediately. Remember this. Look, I wrote here for your help. Lim sup of a sequence an being equal to a means that for every epsilon, an is greater than a minus epsilon infinitely often. Okay? And actually, it also means that an is less than a plus epsilon for n sufficiently large. So, So if you just look at this part over here, the law of iterated logarithm implies that y bar n is greater than 1 minus epsilon, which is a, here's 1 for us, times, I had this denominator on this side, just put it on the other side. So let's see how this actually implies what we want. I want to say 1 for n sufficiently large, and NEC, we have that the square root 2 log n is greater than c. So the law of iterated logarithm implies that y bar n is greater than c divided by square root n infinitely often, almost surely. Actually, I forgot the 1 minus epsilon here. 1 minus epsilon 2 log n square root at some point is greater than c. Just give me a c and an epsilon n at some point is sufficiently large for that to be true, okay? And so y bar is greater than c divided by square root n infinitely often, almost surely, okay? So let's get rid of the almost surely here. So that means that there is there is a set that I'm going to call omega of the sample space such that the probability of omega is 1, and for all omega in omega, we have that y bar n of dot omega is greater than c over n infinitely often. So if we want to get rid of the infinitely often, this means that then there is a subsequence let's call it nk of n such that y bar nk of omega is greater than c divided by square root n for all nk. So the law of iterated logarithms means that the sample average is greater than c divided by square root n along a subsequence, okay, with probability 1. Which is essentially what we said earlier here that we wanted to show. That x bar was greater than c divided by square root n for all n, almost surely. Well, we can show that along a subsequence, okay? So we can say then p hat n satisfies all the requirements of Pn almost surely along a subsequence. Then along the subsequence we have what we need. That is just going to be that jn x p hat n is going to converge to the maximum between z and negative c. And this is not the limiting distribution of the original test statistic. Questions about this? All right. Now, that's the most difficult thing that we did, to be honest. Like, subsampling is quite easy to analyze in this example. Let's revisit subsampling. Subsampling is the estimators were denoted by theta hat, bn, j, where j index the particular subsample we use. And this is going to be the maximum of x bar bn j, which again is the sample mean that you obtain from the jth sample of size bn and 0. I wrote here x bar n bj is the sample average of the bn observations in the j subsample. So what's the distribution of the subsampling root? Well, you write it like this. Instead of Tn, I'm writing TBJ, and it's square root B now, the estimator of size B, minus theta P. Same trick. Replace by the maximum, subtract, and multiply. And then what you see here is something that just immediately tells you that if theta P is 0, the subsampling object converges to a maximum between Z and 0. And if theta P is positive, then it converges to C. So subsampling works. It doesn't have the problems that the Bootstrap had. And it's just exactly the same limit as the original test statistic. And I wrote here, as opposed to the Bootstrap, subsampling provides the right limiting behavior under standard asymptotics based on a fixed probability distribution. Notice that this is exactly the buzz about subsampling, which is the Bootstrap requires this limiting distribution to be continuous in P. And the distribution that we have is not continuous in P, because when theta P, which is a feature of P, is 0, it has a massive shift, okay? It's discontinuous. So the Bootstrap doesn't work well when there are discontinuities. If you have limit distributions that are like, if this happens, then you have this, if this other thing happened, you have that, and stuff like that, then the Bootstrap will be expected to fail. Now, for the validity of subsampling, we didn't have a condition like that at all listed. So it shouldn't be a surprise that subsampling works, because subsampling works only under the restriction that the limiting distribution exists for a fixed P. And for a fixed P, the limited distribution is well-defined and exists, and subsampling works. Okay? So Anderson Guggenberger showed that if a sequence of test statistics has an asymptotic null distribution that is discontinuous in a nuisance parameter, okay, as in the previous example, then subsample test does not necessarily yield the desired asymptotic level. So this statement over here is about this point-wise result may be nice, but the problem is that when you start, looking at subsampling now with a uniform I, then subsampling starts behaving less well. Okay? And then over the years, people study a lot of different settings where the Bootstrap fail and subsampling work, and the Bootstrap fail and subsampling work. And by now, the folk wisdom that people will use, that if there's a setting in which the Bootstrap fails, okay, then subsampling may not be uniformly valid. I mean, it's going to work point-wise, but may not be uniformly valid. It's not accurate because, we're going to see there's situations in which the Bootstrap fails and subsampling still provides a valid approximation. So, but, as a rule of thumb, that's what people just the takeaway. And, if you want to be cautious, is a way to proceed. But it's not an accurate statement. And you're going to see why as we move along. But hopefully it's clear that the subsampling, works point-wise, because the argument, the formality here is exactly the same as the one that we had in the original sample. So we're going to start thinking about uniformity. The problem, not the problem, but a feature with subsampling is that there are two different rates of drift, such that over-rejection and under-rejection can occur, okay? And so, and the problem is when you start dealing with subsampling, what it means for something to be far or close from the truth or from 0 or for the parameter that we care about depends on the rate that you are learning. And it turns out that the full sample statistic learns at a different rate than the subsampling test statistic, okay? So today we're going to be borrowing this notation from Anderson Guggenberger. It's these papers by Anderson Guggenberger are really intensive in notation, so it's not so easy to just learn them. If you just go and grab the paper, start reading them lightly, they have their own notation. And in particular, they're gonna divide the limiting distribution, or the distribution of the data, P, they're gonna just index P by two parameters, theta and gamma. Okay. And they're gonna index the parameter and theta and gamma, because they essentially want to split all the parameters of the distribution in terms of two things. One that is going to be nice in a way, nice, and the other one that is going to be bad. Gamma is going to be the one that introduces discontinuities in the distribution. Theta is the parameter that is nicer. And depending on the setting, that's going to be very clear. And actually, in some settings, like the one that we're going to discuss today, they're going to be exactly the same. But for the purpose of understanding what we're going to do later, I'm going to be using these notations, gamma and theta, even though in this particular example, theta and gamma are exactly the same thing. Okay? It is not the case in general. Most often, the parameter that causes the problem and the discontinuity, which we're denoting here by gamma, is not going to be theta. Okay, it's just going to be something else. But what we're going to do then is we're going to consider sequences of null distributions Pn, okay, along sequences of parameters. Okay, so theta Pn, of course, now is just going to change with n as well. And then we're going to look at the behavior of the full sample test statistic, the one that we obtain, with our full sample, and that's our test statistic, and the subsampling test statistic, which is the one that is going to give us the critical value. And we're going to look at both. And as I wrote here, the complication is that the asymptotic distribution of the full sample test statistic is discontinuous at gamma equal to 0 here. So the remark, and I apologize if this is confusing. Here, theta n and gamma n are going to be the same parameter, but in general, they're different. So I'm going to be using this notation. I'm going to be referring to gamma as we move forward. Okay, drift sequence number 1, gamma n is going to be h divided by square root n. And we're going to study two test statistics. As I said, the full sample test statistic and the subsampling test statistic. Let's do it. Subsampling test statistic. Tn square root n theta hat n minus theta n. And again, remember, this is the maximum x bar n 0 minus theta n. Remember that if we just subtract and take the square root n inside, we have this. And then let me call this whatever, Zn. This is the maximum between Zn and negative h. So this converges in distribution to the maximum between Z and negative h, which we call JH. So now hopefully you understand our notation. JH is so JH is just what I wrote there. I'm not going to write again, but J0 is the maximum of Z and 0, and J infinity is just the maximum of Z and negative infinity, which is Z. Okay, so that's why I wrote J0 and J infinity before, and now we have JH, which is this object. So the full sample test statistic converges to the distribution JH. What happens with subsampling? Well, we have T Bnj, which is square root Bn theta hat Bnj minus theta n. And so let's write things again. This is the maximum x bar Bnj minus theta n. And again, this is the maximum square root B n x bar Bnj minus theta n. And let me call this object over here ZBN. So this is the maximum between ZBN. And here we have square root B times theta n. Okay, what I'm going to do is to multiply and divide by square root n. Okay, so I'm going to have negative square root bn n times square root n theta n. Then notice that then this guy over here is h, and this guy over here converges to 0, given the assumptions that we have about subsampling. So this conversion distribution to J0, which is the maximum between Z and 0. So immediately we see that when we start looking at subsampling along drift sequences, and this is just one of the two that we need to consider, we see that the full sample statistic and the subsampling statistic converge to different limits. Whereas the full sample depends on the local parameter h. Okay, so full sample understands that you're not, exactly 0. This is a drifting sequence that is approaching 0. Subsampling is such that, this sequence is just going to 0 too fast, and it just behaves as if, the parameter value that you're considering, theta p, is 0. Okay, and that's what it's doing. So what are the consequences of this? Well, I wrote here, the full sample, the asymptotic distribution depends on the local parameter h. The subsample test statistic, the asymptotic distribution is for the case of h equal to 0. The claim is that JH is greater than or equal than J0 for all x, where JXP is just the CDF of the maximum between Z and negative h random variable. And so in particular, notice this. JH and J0 are actually the same for any x that is positive, but JH is strictly greater than J0 for any x that is in between negative h and 0. So if you don't see this, and you don't have to see it, let's just make a picture. So the distribution J0 looks like this, where I want to say here there's a mass point. So this is J0. And we just go and do a picture of JH. Okay. Looks like this. Oops. Oh, come on. There's a mass point at negative h. Okay. And this is JH. So you notice here that JH and J0 are exactly the same for any x positive, right? Because it's just the same region of the standard normal. However, between if you grab an x in this area, you have that J0 is actually equal to 0 if you look at this picture on the left. Right? J0 is just 0, whereas JH takes values over here, so it's strictly greater. So it turns out then subsampling gives a good approximation to the right tail of the distribution, but a poor approximation to the left tail. So any statement that depends on things that go on this side are going to work well. Things that depend on issues that are on which the features on this side, are not going to work well. And I wrote here an upper one-sided subsample confidence interval for theta p, okay, will perform well, okay, because it's going to rely on a critical value that depends on distribution on the right. However, if you think more broadly, and here in this slide I just present all possible things you can do, this is not true in general. So first, upper one-sided confidence interval, let CH 1 minus alpha be the 1 minus alpha quantile of JH. That is, this is how the definition of the quantile, okay? 1 minus J of this quantile is equal to alpha. Well, then if you use this critical value from subsampling, which is Z0, and then you compute the probability that your test statistic is greater than the critical value, this converges to 1 minus JH, okay, which is the limiting distribution of the test statistic at the quantile of subsampling, which is Z0. And it turns out that this is less than or equal than this, which is equal to alpha. So in that case, we're good. You want to do a test, doesn't exceed alpha, and the inequality goes in the right direction. Recall that here that we said JH is greater than or equal than J0, so 1 minus JH is less than or equal than 1 minus J0, which is what we're using here, both at the same point. And so this is true because if you just look at quantiles, okay, the quantiles of the test statistic and the subsampling thing are exactly the same whenever alpha is small. Like if you're just doing a test, a 5% test, well, this is just going to work. Whereas the quantile of subsampling is larger for any other alpha. But in either case, the subsampling quantile is always greater than or equal than the subsampling of the test statistic. And that's what we need to do, that type of tests. But suppose that you consider an equitail or symmetric two-sided confidence interval. This is going to perform poorly. So let C bar H be the quantile defined like this. 1 minus GH at the quantile plus JH at negative the quantile is equal to alpha. Then the probability that your absolute value of your test statistic is greater than this critical value you obtain from subsampling. Now where you replace, subsampling is J0. So this is going to be C bar 0. Well, this converges to the distribution. This guy is JH. So you're going to have JH here, like as in this case, but evaluated at the subsampling quantile. Well, then turns out that if you just look at this, since this guy is positive, 1 minus JH at Z0 bar and 1 minus J0 at Z0 bar, they're the same. They're the same because if you just look at this distribution, if you just grab it, I don't know, Z bar 0 here, Z bar 0, then this is JH and this is JC. And we said if the critical value is positive, these two are the same. Okay? So then this part is the same. But the last part is this guy is greater than or equal than that. And actually strictly greater if C0 falls between 0 and H, right? And so this probability exceeds alpha and it leads to over-rejection. I wrote in the example, if you take H equal to 2, the 95% quantile of the distribution of the maximum between the normal and 0 is 1.63, whereas the 95% quantile of the distribution of the maximum and negative H is 1.96. This is the quantile that you want. This is the number that you want for your inference. This is the number subsampling gives you. Okay? And so it's just too small. So you see here that, it's not so obvious that you can say that subsampling fails all the time or whatever. Is more about understanding what is the driving feature. And sometimes it's just going to be too big, but too big is good. And sometimes it's just not going to be big enough and that's not good. It depends on what you're doing. So I know some of these inequalities and all this is confusing. Believe me, it's not difficult. It's just confusing. Like, this today at lunch, I was just eating a sandwich and I was just making sure that the slides didn't have typos. Okay, corrected some typos that I had before. And whenever I get to these things, and it's like, what is this? Why is this greater or smaller? Like, I'm always confused because it's just not natural until you just start doing the pictures. In particular, if you just stare at these pictures and you just do them, then you realize that everything makes sense. But it's not immediate. See, if right now you're feeling lost, that if I ask you, is this greater than that or is this smaller than that, you go like, well, that's expected behavior, okay? But once you get used to it, my point is that there's nothing sophisticated behind this, just understanding how things perform. But the moral then is that when you consider this drifting sequence, subsampling may over-reject, okay? If you care about, for example, this type of inference problem, which is an equitail one, then subsampling will over-reject. And the thing is that that's not the only sequence. There's another sequence that is important for subsampling, which is the sequence that learns at rate square root b. So what happens in that case? Let's do it. Just take the full sample test statistic. We're going to do the same business. Square root n, theta hat n minus theta n. And let's try to be efficient and skip one step. So this is square root n x bar minus theta n minus square root n theta n. And now I'm going to do the same trick that I did before. I'm going to multiply and divide by square root b. And I'm going to call this guy over here Zn. And then once we use that trick, notice that this is what I'm calling G. This is coming over here, right? Notice that the square root Bn times gamma n is G, which gamma n is the same as theta n. And now, where is this going? It's going to negative infinity. So the full sample test statistic converges to Z, which is what we call J infinity. For the full sample test statistic, this sequence is going to zero so slowly, okay, that, for the purpose of this full sample test, is like if this sequence is a positive theta, okay? Then the subsampling one, and let's again skip one step. Now this guy here is G. So this conversion distribution to the maximum between Z and negative G, which of course we're going to denote as JG. This class is really boring. Like first lecture, we were doing this business of, a square root n and the sequence and this and that. And then we find ourselves in lecture 12 doing essentially the same thing. Okay. So I'm just exploiting the only capital that I have for teaching purposes. Anyway, the main thing is that, again, J infinity is greater than JG, okay? And again, if you want to do a picture, do the picture. Here you will have J infinity is a normal. JG is just gonna look like this again. So there's all this area where J infinity is gonna be strictly larger than JC, and there's all the other area that is on the side where they're going to be the same. But the side of the inequality is exactly the same as before. Before, we had JH was greater than or equal, which was the full sample test statistic, greater than or equal than J0, which was subsampling. Well, now we have J infinity greater than or equal than JG, which is subsampling. So the same type of inequality, the same type of result. Everything we wrote in the previous slide applies for this case over here, just that everything is shifted. So asymptotic size of subsampling. We're going to consider family of distributions bold P, okay? And now what we're going to do is, instead of like just defining P in general, what Andrews and Guggenberger do, which is a way that is done in some other papers, and today I devote this class to expose you to that, is, as I said, write the family of distributions as a function of theta and gamma. And actually, if you just look at the paper, they actually split things into 3 parameters for reasons that I don't want to cover today. So, and then gamma here could have infinite dimensional components. These are not like finite dimensional parameters. So you can actually describe, if there are error terms and those error terms have distributions that you don't know, well, you put that as part of like gamma, okay? And that's part of the reason why they have 3 parameters as opposed to 2. But anyway, for the purpose of what I want to say now, there are 2. One is the thetas, which is the parameters you want to do inference on, and the other ones are the gammas, which are the parameters that introduce the discontinuity. And so the exact size of the test that reject, theta p equals to theta naught, okay, when the test statistic is greater than a given critical value, is this. It's the supremum over gamma of this distribution given this. Notice that, I wrote it here. This is so convenient. P naught, you can write it as P theta gamma, where theta is equal to theta naught, and gamma is just in the parameter space. And so this means that statements that we wrote previously, like supremum of P in bold P naught, is exactly the same as supremum of gamma in gamma P, okay? Because there's just 2 different notations for writing essentially the same thing. I've been using this guys use this, okay? So they're going to write the asymptotic size using this supremum over gamma. The asymptotic size is the limit of the exact size. So you say lim sup of essentially the same object, which is what we did before. You first take the supremum and then take the limit. And our interest is in the exact final sample size, okay? And as I said just multiple times now, we use asymptotics to approximate this. Uniformity over gamma is necessary for the asymptotic size to give a good approximation of the finite sample size. And if you go, once you understand, hopefully you understood everything we discussed about uniformity before, you're going to see that a lot of these type of statements are written for the people that are less clear about this. And if you understood well what we covered before, these are going to sound like, sure, of course, okay? But it's good in papers to clarify exactly where we're doing certain things. And as I said before, by now people are used to these uniformity things, and perhaps when these papers were written, people were less used to pay attention to this thing. So they would immediately ask, why do you have a supremum there? What do you need the supremum? And so on. So there are discussions like this in the paper about why it's important to consider the supremum before taking the limit. But we already discussed that, so we know that. So the important thing is that what we learn in this example holds in general. And this is the result in Andrews and Guggenberger. I just show like the simplest example positive, which is a parameter at the boundary, but a lot of the features that we learn in these simple examples hold in general for any problem. So let JH be the asymptotic distribution of the original test statistic under the sequence gamma n, okay? And where H is going to be the limit of square root n gamma n, as we did before, and G is going to be the limit of square root b gamma n. So we're going to use h and g. Notice that h belongs to any number between 0 and infinity, including, so these papers are going to work with the standard real numbers. Infinity is an important number, okay, because sometimes we do get infinity, and g is just going to be taking values between 0 and infinity as well, okay. Under the same sequence, we're going to let jg denote the asymptotic distribution of the subsampling. So we have two distributions. We have jh, distribution of the original test statistic, which we have jg, distribution of the subsampling thing. So the set of all possible local parameters jh, okay, is denoted by capital GH. This should have said GH, sorry. It's denoted by capital GH, and it's this. Notice this. It's just all pairs of GH such that G is 0 if H is finite, and G could be any number if H is infinity. Say it again. G is 0 if H is finite, and G is anything if H is infinity. Let's just go back to what we did. The first sequence we did is this one. Here we got H, which was a finite number, okay? When H is a finite number, G is 0. This is what we obtain, okay? And then we did the other case where we said, okay, let's G be any number. In that case, H is infinity, okay? So when you look at this set, if H is infinity, G is any number. If G is 0, if H is finite, then G is 0. It's exactly the two cases that we looked. Importantly, this matters. G is less than or equal to H for all H in GH. You see that because, here H is finite and then G is 0. So it's less than or equal than any finite number. And here H is infinity and G is 0. So of course they could be the same. It could be that J is 0, infinity here. It could be that H is 0 here and G is 0. But you are never going to have G strictly greater than H. So in the previous examples, we got, GH 0, 0 and infinity, infinity. By the standard point was asymptotics. That's exactly what we did before we did uniformity. And then we got 0H and G infinity used in drifting sequences. All these 4 points fall into this class. And so, the lemma that you're going to find in Anderson-Gumberger says, suppose that for all H and all sequences, Tn converges distribution to JH under this sequence P theta naught gamma n for some distribution JH, then the asymptotic size of this test that rejects whenever T is greater than the critical value is this, is 1 minus JH, right, which is the limiting distribution of the test statistic, at the limit of the subsampling critical value, and take the worst possible sequence, okay, inside this set that is GH, okay? In our case, we consider two cases, but there could be other combinations in general. But if we just look at and stare at this formula over here, if you take without the soup and you look at this thing, this is exactly what we did in the example. Okay, and then now you're saying, okay, out of the examples, I just want to look at the at the worst limiting thing that I can obtain. That will depend on the problem. Most often, it's not going to be something in between, but this you can typically analyze theoretically. Sometimes if you want numbers, you can simulate this or whatever. It depends on the setting. But in particular, the asymptotic size of subsampling is going to be less than or equal than alpha if and only if the subsampling critical value is sufficiently large. And by that we mean it's at least equal to the quantile of the original test statistic. It could be larger. So sometimes subsampling could be conservative, okay? But you need this to be at least equal to the quantile that you want. The general results can be used to analyze a lot of examples. Here I wrote, in an IB regression model with potentially weak IBs, all nominal 1 minus alpha one-sided and two-sided subsampling tests concerning the coefficient of an exogenous variable based on two-stage least squares estimator have asymptotic size equal to 1. So weak ID is a problem with subsampling performs really poorly. You just go, applies these formulas, okay, and then you take the soup. That's 1. In models where, say, parameters are restricted by moment inequalities, subsampling tests and confidence intervals based on suitable test statistics have correct asymptotic size. So you can use this, that it doesn't matter, what of the situations that we previously described you have. Subsampling always have this feature that the subsampling critical value is at least equal to the thing. So, so it's, at the end of the day, it's problem specific. If you're in what was often called an irregular problem, okay, a problem that is not as simple as not as smooth or exhibits some discontinuities, weak IV is certainly an example. Pre-testing situations are an example. Moment inequalities are examples. Any situation where you have estimators that are maximum and minimums of things, okay, like auctions and whatever, are another example. All these situations are cases that are going to fit into this quote-unquote discontinuous cases, and subsampling may or may not work well uniformly, depending on the setting, okay? So, as I said, this idea that the bootstrap in all these cases fails, point-wise, okay? Subsampling works, point-wise. But uniformity depends on the setting, okay? And in some settings, like moment inequalities, part of the reason that, is always a way out is because people know that generically they work well. And if you don't know, of course, there's always larger hopes for subsampling to work well than for the bootstrap to work well. Comments. The approach given above is based on sequences of nuisance parameters, and it requires verifying certain assumptions for all possible sequences of nuisance parameters. So when you look at a statement like this one over here, you may think that it's really easy to prove and so on. These proofs are sophisticated, and they were definitely non-trivial, okay? So in particular, proving that a test controls asymptotic size typically requires to argue that it is not possible to find a non-stochastic subsequence of parameters such that this happens, okay? So proofs sometimes go exactly that way. Suppose that there was a sequence where this happens, okay, and then you run into a contradiction. Is that one way to do it? But anyway, I said a different approach, which is something that I mentioned earlier, includes the one in Romano and Sheikh, which was published in the Annals, who showed that subsampling tests are valid whenever the family P satisfies this thing over here. So if you just remember anything that what we said earlier, notice that before we didn't have this supremum over P, we had something like that. JB converges to JN, or the difference converges to 0. Well, here they say like, well, you want that holding uniformly over P, okay? And so whether you can prove that or not in some settings, sometimes, there's always some tension or some fight depending on who you talk to. If you talk to somebody like Asim Sheikh, he will say, okay, it's just easier to think about this type of conditions. You don't have to be thinking about all possible subsequences. Talk somebody like Don Andrews, who will say, well, it's easier to think about subsequences and proving things this way. It's just different tools, okay? In terms of conceptually, they lead to the same place or the same answers, just by exploiting different mathematical tools at the end of the day. Notice, before I conclude, that I said earlier that subsampling works generically, or is more likely to work well than the bootstrap. However, there are two things that should not escape your mind. The first one is that subsampling has this block size Bn, and Bn is difficult to choose because there is no optimal way of choosing Bn. So it becomes a tuning parameter that is at the discretion of the researcher. And, if you ask people, I'm saying by that, apply people that, dislike subsampling, they will say like, oh, tell me what's the number that you want, and I'll give it to you with subsampling by just choosing B accordingly. And, even if you're not trying to cheat, suppose that you're really trying to deliver an honest answer, as a researcher, is quite problematic if you, try a value of B and then you change it a little bit, and then your numbers are totally different, because now then you don't know what the actual numbers are because you don't have a good way of choosing B. So that would be the first thing. The second thing is that when both are valid, okay, so if it happens to be the case, then you're in a situation where the bootstrap is valid and subsampling is valid. The bootstrap tends to work better. We know that, for example, the bootstrap may lead to the so-called asymptotic refinements. But sometimes, even in settings where you know that the bootstrap does not offer an asymptotic refinement, the bootstrap works better anyway. And this is still, people don't know why that's the case, but it's often in simulations the situation that the bootstrap works better. So it's that one of these situations where you shouldn't jump immediately to say you know what, I'm not even consider the bootstrap because I know subsampling will generically work more often. Well, because if the bootstrap works, you save yourself from having to choose a block size and defending your block size to your audience, okay? And two, you may actually be having better results by using the bootstrap. But anyway, that's it for today. So you guys tell me what you think.